This is Mrs. O'Neill for AP Chemistry, Chapter 14, Section 6, Part 1, Reaction Mechanisms, the Notes. So here is an intro lesson that you should have watched on elementary reactions. Here are my notes. The elementary reactions is one step in the overall reaction mechanism. As a reminder, even these reactions, these individual reactions need enough energy and the correct orientation for the reaction to occur. Nice little flow chart as he always does. He talked about these collisions, and remember, these collisions are between these atoms or molecules that make the products, right? Between the reactants to make the products, but they have to have enough energy and that correct orientation. So remember, stoichiometry can be predictable from the balanced equation. However, not the rate law. The rate law has to be measured. It cannot be predictable. We have to measure the rate. We have to get the data. We have to manipulate that data to figure out what that rate law expression, because every single reaction has its own. So reactions, the overall reaction, let's say, does not show us the whole picture. This is why these reaction mechanisms are very, very helpful. And they're also helpful in understanding where those intermediates come from, why they're made, why they're used up, and why they're not part of the overall reaction. So reactions are broken down into steps, and these steps are called elementary reactions. So a unimolecular reaction means that there is only one reactant forming those products. Bi would mean there's two atoms or two molecules have to hit each other with enough energy and have the correct orientation in order to make those products. And a termolecular elementary reaction means that there are three atoms or three molecules coming together to form products. These are very, very rare. So the other intro lesson you should have watched was on the multi-step reactions. So again, my notes include his understanding or his example, his analogy of making a train, right? You have all of these parts of a train, and now you have to build them step by step in the correct order in order to build that train correctly. So the same thing happens in chemical reactions. So that's why we have these intermediates along the way. If you don't have the correct intermediate, well, the next reaction, whatever that reactant is that needs to react with that intermediate from the first step, might not form correctly. So in chemical reactions, there's a step-by-step process. Again, a nice little flow chart showing you that there are multiple steps for the overall equation. Again, these are based on the collision theory, as well as the rate law now can be based off of, or we can measure and use one of these elementary slow steps to figure that out. So what is stoichiometry versus the rate law? Again, he talked about stoichiometry. We can just balance the equation and figure that out. But with the rate law, we need some experimentation. So the rate law is measured because it is based off of the slowest step of one of those steps in the reaction mechanism. So how can we figure this out? Again, we figure this out knowing that rate law of that slowest step. He talked about the Kelvin and about how leaves go from CO2 and make that sugar. How does it do it? Well, again, that reaction is going to stop at different points. So he figured out that there were some kind of intermediates. There were some things that were not included in the overall reaction, but they have to be included at some point to be used in a different reaction. So that's called the Kelvin cycle. So for those of you who might be moving on to biochem. So you should have also watched the next intro lesson on reaction intermediates. My notes include, well, the most important chemical reaction is these cells, okay? So again, a lot of biochemistry going on here. So again, this happens in steps, and there's these intermediates along the way. They are very important. Again, a nice little flow chart. And his analogy was about a caterpillar becoming a butterfly. Again, a lot of things in nature even happen in a series of steps. It doesn't go bada bing, bada boom. Everything either happens in phases or steps. So the overall reaction, again, we need to use experimentation. So this particular equation is made up of two steps. So do you see the same substance as a product and then a reactant? And I always like to say an intermediate starts off as a product and then as a reactant in a new step, in a different step, in a subsequential step. Oh, I can't say that word. That would be called the intermediate. So again, they cancel out because they never appear in the overall equation. So here he gave you an example of crossing out those intermediates. And again, they do not appear in that overall equation. He calls it step 3. I'm not really fond of that. I'm more fond of this step 3 should be really called the overall reaction. So how do we figure this out? Well, that's the chemistry, and we do it by experimentation. And again, this is why a lot of biochem has these experiments with it. The next intro lesson was on the rate limiting step. I like to call this the rate determining step because to me it determines the rate of the reaction. However, think about the limiting reactant problems that we did in Chem 1. Aha, well, those limiting reactant problems, well, that reactant limits us from producing product. Well, the rate limiting step or the rate determining step tells us how much of that reaction is going to go or how fast that reaction is going to go. So again, my notes include his example of these cars. So again, I call it the rate determining step. Gives us this analogy of cars going from A to B to C. Okay, nothing slowing them down, so they're all going at the same rate. However, if we put an easy pass in, right, now we need to collect some money, but that easy pass just still kind of lets everybody go at the same speed. Now let's put a toll booth in. Well, at that toll booth, the cars that need to stop and actually pay the toll by cash is going to slow down that rate. So that would be the toll bridge here, or the toll stop would be the rate determining step. So again, that nice flow chart, and that rate determining step is going to be one of those elementary steps, but it has to be the slow step. And I will remind you that no matter how many elementary steps there are to the reaction mechanism, only one can be the slowest step and the rest of them are considered fast. So in this case, again, he gave you a nice little analogy of that toll and the cars going through and what would be the rate determining step. So that rate law then can be based on that rate determining step. If we know which step is the slowest step, then we know that that's going to be the rate determining step, and we can base our rate law on that. Again, here's our chemistry example, and he gives us that there's a rate of this guy and a rate of this guy. And again, each of them also has their own rate constant. So again, if the first step is the slow step, then that would be considered the rate determining step. So, look at our rate law expression. K, concentration of the N2, because there's two N2s, squared, right? So NO2 squared, because there's two of them. So again, and that rate law expression is based on the reactants alone. So notice there's no intermediates in that overall, first of all, in the overall expression or reaction and in the rate law expression. So again, that rate law has no intermediates, and I want to remind you that it's always a product first and then a reactant later, and they will cancel out. So another example, he dealt with equilibrium. And again, that rate law has no intermediates and it's based off of the slow step. So notice rate equals our K constant, okay, which is K2. He just tells us that it's the second equation, N2O2 to the first, because that's our coefficient, times the concentration of O2, again to the first power. So overall, this reaction or this rate law expression would be second order. So equilibrium, just as a reminder, and we're going to learn this in the next chapter, that the rate of the forward reaction equals the rate of the backwards reaction. So we talked about this general equation and how that overall rate law of this equation can be simplified and substituted, and again, there's no intermediates. So on to your packet notes. In this section, you're going to examine these reaction mechanisms, that the step-by-step pathway leading these reactants to products. So first I have an example. We're going to make some lollipops. Well, what do we have to do? Well, we're going to take some sugar. We're going to add some water. We're going to make a simple syrup. That would be my first step. Second step would take some that simple syrup and mix it a little bit with the dye to make it a different color, add some flavoring, and now I'm going to pour it into some molds. My third step is to let it cool. And voila, I have my final product of my lollipops. So again, I made these lollipops in steps, just like reactions, okay? So pause the video, fill in the words, and then play to hear my words. And again, read as you write. So this reaction mechanism is a process by which the reaction occurs. There's three requirements though, right? The mechanism has to predict the overall observed rate law. In other words, one of those steps have to be slow and has to be that rate determining step. Of course, it has to add up correctly, right? It has to add up stoichiometrically correctly to equal the balanced chemical equation. And of course, in the chemistry world, it has to be believable. So read over this, and hopefully that this makes sense. So these elementary reactions, again, the reactions that occur in those single steps can be unimolecular, bimolecular, or termolecular. So if it's uni, it's got to be first order, bi would be second order, and ter would be third order. And again, that termolecular, they are very rare because if you have to have three things that have enough energy and hit each other at the correct orientation, that's hard to do. So give this some thought. Hopefully that makes sense. You have two reactants, so it's going to be bimolecular. Again, these multi-step mechanisms means that these reactions occur in more than one step, but the overall reaction has to be equal to the sum of those elementary steps. So again, just like that delta H that we did way back in the day in chapter 5, right? Delta H, to figure out the delta H of the overall, if they give you multiple steps, you got to figure out the delta H of each individual step and then add them up at the end. And I want to remind you that the intermediate is a product formed and then it's consumed later as a reactant, and it is not part of the overall reaction. Oops, sorry. Where am I going? I apologize. Here we go. So this would be an equation or an energy diagram relating all of those multiple step reactions. So instead of just one hump, right, one hill, now we have 1, 2, 3, 4 hills. We got 4 hills to go over, which means we have 1, 2, 3 intermediates, and we have 1, 2, 3, 4 activated complex. So that's really important. Okay, so can you answer the following? Even though you already know this answer, let's think of another analogy. So read over this and see if you can answer questions 1, 2, and 3, and you might have to do a little bit of math. Hopefully you got that answer. Hopefully that makes sense. Now let's look at the math. And what did you get for number 3? Aha, well, if we notice, the slowest step equals the average step. Let me do it this way. The slowest step really equals the average step. So that should make sense. So the slowest step really determines the rate of the overall reaction. You can only go as fast as the slowest person. So again, that rate determining step is going to be the rate of the overall reaction because you can only go as fast as the slowest step. So these are the rate laws, and these should make sense. So if these are your elementary slowest step of your reaction mechanism, this would be your rate law expression. So rate equals your K constant, multiplying all of the reactant concentrations, and those exponents are now your coefficients. Okay, see you in class.